So the first speaker is going to be Grace Heath, and she's going to be telling you about work she did at an REU, a research experience for undergraduates up in Rochester, New York. So for the current students who are here, I encourage you to think about doing an REU. There's lots of opportunities. I get notices all the time. So now's the time to be thinking about next summer if you want to go somewhere and do some research. Take it away, Grace.
All right. So for those of you who don't know, my name is Grace Heath, and I did an REU at RIT with Dr. Scott Franklin, and our REU was funded by NSF, the National Science Foundation, and I did this research under SMERC, which is the Science and Mathematics Education Research Collaborative, which is under CASEL, which is the Center for Advancing STEM Teaching and Learning Evaluation. It's a mouthful. But that's all at RIT. They have a huge department for physics education, which is what this project's about, and specifically identifying epistemic frames in student problem solving. So the first thing we have to talk about is what is physics education? We don't really have a physics education field here at Loyola University, but it's pretty much like any other physics research. Instead of asking what are you trying to measure, we ask what should students be learning. Instead of asking how are you going to measure it, we say what are students learning. And in physics research, when you say what variables are you going to change, we say what instructional approaches improve student learning. So it's all about the classroom and how to increase student learning in physics. So before I begin, the research I did this summer is just a small portion of a larger research collaboration, and it spans from RIT to DePaul University, Cal Poly Pomona, Kansas State University, and now here at Loyola. And as of right now, the research I'm continuing this semester, I am actually working with the people at DePaul University, and we are specifically looking, I'll talk about this in future work, but we're focusing on kind of a different route than the other researchers, but we are still a part of one collaboration. So the first thing we have to talk about is what is a frame. A frame happens in everyday life with all of us. It's a way of thinking or your state of mind. So if I'm up here giving my presentation and someone was to raise their hand and say, hey Grace, I hate your presentation. Not really like that, but hey Grace, I don't really like your titles. Like they should be more detailed or something like that. If I was in a defensive frame, I would say, that's so rude, I can't believe you told me that. You know, I would get really offended. But if I was in a constructive frame, I would say, thank you for saying that, like, I'll take that into consideration for my next talk. So that's kind of how we navigate frames in everyday life. But you also navigate frames in the classroom, and these are epistemic frames. And these are specifically how a student understands, approaches, and makes decisions about problems, specifically using physics and math, physical concepts and mathematical tools. So that's kind of how epistemic frames work. An example of that, if I was to give a question and say, like, I need you to find the numerical value of gravity, and I gave you a bunch of numbers, right? You could say, all right, I'm going to calculate this, I'm going to put it into my formula, and I'm going to use computation and find this. But you could also take another route and say, well, I know that gravity already equals 9.81 meters per second squared. So you can just recall that information from physics. You don't necessarily need to go through the computation. So these are kind of like ways how students go through problems in the physics classroom. It kind of just depends on the student and what knowledge they've learned before doing that problem. So the four frames we look at are derived from a two-axis framework, which you can see it's the algorithmic and conceptual. So algorithmic is more computation, conceptual is more ideas. And then we have our subject matter on the y-axis, which is physics and math. Pretty self-explanatory, and we'll get into the definition of those frames in a second. Our four frames are algorithmic math, conceptual physics, or it's algorithmic physics, conceptual physics, algorithmic math, and conceptual math. So what's the purpose of doing this? Why do we care about physics education? Why do we care about this project at all? Who cares about epistemic frames, you know? Well, we want to learn and gain insight on how students process information, how they solve problems, and how they think. And from this, there could be pedagogical or curricular reform in the classroom, but that's not our main goal. We haven't, because this project's brand new and I started it in June, we're still in the beginning processes. We don't even have a specific research question yet. We're pretty much just laying the groundwork for papers and stuff like that, but we are still coding video data, so everything's in the works. But, you know, pedagogical or curricular reform is always a good thing if you can make the classroom a better environment for students. So hopefully that happens. So for methods and context, we are specifically looking at an upper division electricity and magnetism physics course, just like we have here at Loyola. Next spring, it's a 300 level course. And in this course, we're looking at activity-based tutorials that the University of Colorado at Boulder created. And these tutorials, we do these here. These tutorials are kind of like problem sets that you can do every week after lecture to kind of summarize what you learned and to make sure that you know how to do these topics in practice. And then we also look at individual problem solutions. So everyone in our collaboration has done all the tutorials. We've all individually solved every tutorial that was given to us from Boulder. And we look at how us as researchers solve them, people who know how to do the physics. We look at how we solve them, as well as the students who are currently learning the material, and that comes from video recordings of groups at Kansas State University. And this is groups of 3 to 4, sometimes 2, and they're just working on these tutorials in class. And sometimes we get to look at the lecture too to see, you know, we can piece together what they've learned with the tutorial and see what gaps are there or why they're not in a specific frame that we were necessarily in when we solved the problem. So my goal for the summer was to create a code book. So this is like a blank code book. And a code book is used to essentially lay the groundwork for a research project. So once this is filled out, it can be given to researchers across the country who have been given human subjects training through IRB. And they are able to look at this code book without reading any literature, without having any knowledge about physics even. Like, I could give this to one of you and you could say, all right, like, I have this code book, I'm going to code this video data now. And that could happen. It's just a matter of filling it out. And the first thing you have to do when creating a code book is establish inter-rater reliability. And so inter-rater reliability asks the question, do researchers agree? Are we all on the same page? Are we coding the same way? And so what we did is we coded our video data in an open source software called Boris, and it deals with coding audio and video data. So I worked with 4 researchers, and together we looked at some of the beginning of the video data, and we coded it in Boris. Now, without the code book, like, how do you code it, right? We kind of just guessed. We were kind of just saying, all right, let's just try it, you know? It couldn't hurt. So we all coded it just with our knowledge of physics, and it actually came out that we're 95% consistent in the fact that we were coding the same things and we were getting the same results as students, which is great. So now we have inter-rater reliability, and now I can say, all right, so we all know what we're talking about. We all know, you know, we all know how to code this video data, but we can't put it into words yet. We don't necessarily know what it means to have inter-rater reliability. So through that, we also have to frame map to fill out our code book. And frame mapping, it sounds complicated. It's really not. It's really just looking at the different sections of a problem and your solution and saying, what frame was I in at this specific point? So let's go through this problem. So in the year 2240, a bicyclist named Thomas gets lost east of Boulder and gets a flat tire. Thomas pulls off the tire and then consults his tricorder to find out what life forms are nearby. However, the flat tire has somehow been charged with uniform linear charge density. The tricorder complains that the electric field from the tire is very annoying. Your goal is to calculate the electric field produced by the electrically charged tire if the tricorder was placed on the z-axis. So, Dr. Ching Ryan, who's at Cal Poly, actually solved this problem for us. This is her solution here. But what does that mean? What does it do for us? How is that frame mapping? Well, we're going to go through it. We're going to go through her thought process together and frame map it. So the first thing she did was, okay, I heard the words electric field. I'm just going to recall my electric field equation. So that's where that is. She's using knowledge from her physics background and appropriating that to mathematical formulas. And that's what we call algorithmic physics. Next, she says that by symmetry of the charge distribution, one can see that E components in X and Y direction all cancel out, leaving only EZ to be non-zero. So she's saying, all right, I know conceptually that with this charge density, that they're going to equal zero, right? She's using those concepts to interpret a physical system. She's saying, what about physics do I know that can simplify this physical system to help me? And that's conceptual physics. So next, she does a lot of math. She does a lot of computation. And so over here, you can see that she did find that X and Y are equal to 0. So she didn't have to do that because she found in her conceptual physics frame that they are going to equal 0. But she double-checked herself, always fine, and she did find that they were 0. And then over here, she did find her Z component. And so computation and that procedure of math arithmetic, all of that is algorithmic math. It's kind of the easiest one to define because if you're doing something in your calculator, if you're solving an integral, that's all algorithmic math. Okay, and so conceptual math, she also says that using symmetry, we know half the area under the curve is above 0, half the area under the curve is below 0, total integral is 0. And that's kind of her checking herself for a second time. This is kind of just for the sake of the example. Not always will you find that the X and Y components are 0 3 different times, but that's fine. So her conceptual math is all about saying, like, okay, I know, if we back up here, we see that the cosine and sine are in that integral right there. And so what she did was she saw that the graph of those functions will make it equal to 0. And so she just used her mathematical concept to make sense of the problem, to simplify it, make it easier for herself. And that's conceptual math. So after all of this, I developed a full code book. It's not very important to read it just because there's so much information on it. But here there's the codes, all 4 frames, the keys that we use in Boris. We have our literature definitions, which comes from about 30 academic papers that I read over the summer and kind of combined all of that into these more simple definitions. And then we also have lab definitions, and these lab definitions serve as kind of a representation of what we feel these frames are in our specific research collaboration. And that comes from the video data, from the frame mapping, and just from conversations between all the collaborators. And then we have examples, and those are actually my written examples from tutorials that I solved, and that's to see what they look like on paper, just to give an idea. We also have video examples. Those are timestamps from our data, where you can go look and say, what does this look like when a student is in this frame? We have that. And then we have coding examples, which kind of help push researchers in the right direction of how to code something. So if they are recalling an equation, they're going to be in algorithmic physics. So it's not necessary for them to go back and look at these timestamps if you have little hints on the side. So that's kind of the purpose of the code examples. And so in summary, I developed a full code book that laid the groundwork for our research, and I identified text and examples for each frame that can be sent out across the country for any researcher who wants to be a part of our collaboration. And this semester, I am currently doing research still, and we have about 66 hours of data that's going to take almost 130 hours to complete, because you want to give 10 minutes for every 5 minutes of video data you have. And specifically, our collaboration with DePaul University that I'm working on right now, we're specifically looking for disagreements in frames. We want to see when people say oh no, I think we should do it this way, and another person says, oh well, I see it this way. How do they navigate that? How do they make these decisions? that's what we're looking at, and we are also working on publishing a paper for the Physics Education Research Conference that I am fortunately first author on because of the code book that I made. Shameless plug. And so yeah, that's like pretty much, that's it. Are there any questions?
So did y'all film students solving the problems and then go back and review the footage?
Yes.
Okay.
So the video data is from Kansas State University, and in 2015, the professor who, Dr. Sayer, she's in our collaboration with us, that was her class that she taught at Kansas State. And she contacted IRB, which is just this program that approves working with human subjects. And she asked, hey, can I use this video data? She got consent from all the students to use it, and so now we get to look at it for our research.
So how do y'all, identify if they're using conceptual physics or algorithmic physics?
That's the hard part. So it's all about that iterator reliability. So I could think that it's in conceptual math, but someone else could say, like, I think they're in algorithmic physics, you know? And it's all about working with other researchers and kind of using consistency to establish what frames they're in. Normally you can actually tell. It kind of seems difficult to say, like, oh, well, what if this happens? Which, that's kind of what we're looking for now. We're kind of looking for the things that it's hard to tell, because that's where, like, the most interesting data comes from.
Are you transcribing these videos as you're going through the code book, or are you purely just like looking at 5 minutes of footage and then making some?
So in Boris, fortunately, since it's an open source video and audio data coding software, we get to have the video here. I have a screenshot. So the video plays here, and as it goes, this is like our key, it's hard to see, but like our keys from the code book are here. And so at 14 seconds here, they're in algorithmic math, I would press capital M, and that would code it. That would say this timestamp is associated with algorithmic math. So we don't have to transcribe it because we have the video right there in the data, and we are associating the frames with timestamps.
Are the students talking or?
Mm-hmm.
Oh, okay. Are
Yeah.
they explaining it to someone?
They're working together, so they're all talking while they're solving it on the whiteboards too. And that's why they have the whiteboards set up as well, because with the whiteboards, if they stop talking, you can still see what they're doing on paper. And that way we're still able to continue coding even if they stop talking.
I'm not sure if you said this, but what was your sample size of students?
So we have about, I believe there's around 20 students in each day. So that's, oh wait, it's back here. So 61 days at 20 people for each day. And so some of them, the students sometimes do repeat, but each day we consider a new sample set, just because it's a different tutorial each day.
So would you, so this is data all from one university in Kansas State,
Yes.
right? Would you in the future intend on spreading that to different tier universities too?
Yeah, so we actually want to do that. Actually, Kyle, who's in our collaboration at DePaul University, he is taking this course right now, and he is journaling about his experience, and we've submitted it to the to IRB for approval. So we get to use his journal about E&M for our research data now. Which is super cool because it's like a first-hand account of everything he thinks about. And he knows, because I have the code book, he knows when he's in certain frames. So he gets to frame map all of his stuff. He gets to write about what he's thinking, and we get to use that for data. So we already have something at DePaul University, so it's different from our Kansas State University data.
So you said you're looking at when two people disagree on how to approach a question, and how they after that navigate through that question. After getting all of this data, what do you want to do with it? What are your next steps?
That's the fun part. We don't know yet. Because I just started this in June, this presentation is pretty much everything that happened from June to the beginning of August. That's everything I did at my REU, and I'm continuing this research for college credit now, and we don't know where we want to. That's like the beautiful part about it, that we just like, there's so many things that we could do with it. So we're kind of going through the data, coding all of it, marking down, you know, where students are disagreeing or where there's interesting little debates. And we mark that down, and then we can go back and we can start finding patterns between those groups. So it kind of just depends. We're just going through video data right now to see those patterns and find out where we want to go. But it will all be in our paper by June.
So I've noticed that you have a different type of conceptual map, conceptual physics on an XY graph. Does
Yeah.
that mean, or at least in the future, are you planning to, if you're not doing now, like have some place where you can like have a crossover between algorithmic physics and conceptual
I
physics?
knew you were going to ask that. I just knew it. Okay, so it's not. So the way the graph works is, if you're in algorithmic physics, you can be like completely in algorithmic physics, but you could also be, you know, leaning towards algorithmic math,
Yeah.
right? So that's kind of how it works. What was your specific question?
Well, I mean, just that, like, is there a way to map, like, how, using the Bohr scale, like, how close algorithmic physics, this kind of action that a student's doing is to algorithmic math, but it's still
So
algorithmic.
fortunately, Boris, you can double code. So you can say they're both in algorithmic math and algorithmic physics. You can say that they're in 2 and 1. And that's another thing that we're looking for. We're looking for people in like double frames and people who like, we can't tell what frame they're in. We're also acknowledging that and taking note of that to go back and look at. Because we want to find that out.
What happens if a student doesn't know how to solve a problem or makes a mistake?
So there are actually a few instances where that happens in our video data, and the professor comes up and just, it's kind of like a tutoring session when that happens in a way. They ask questions to try to get information out of them instead of just saying like, oh, this is how you do it. They say like, okay, well, what do you know? And that's how we code it. We code it how they are learning how to solve this problem. So if Dr. Sayer says, okay, well, what are you given? And they recall 3 equations, oh, that's algorithmic physics. So we still code it the same, it's just, they just have more help. The group kind of just expands when the teacher comes and helps them. Anyone else? Okay, thank you.